In this podcast, we're going to talk about Graham's law. Specifically, we're going to talk about effusion and diffusion. Effusion describes the passage of gas into an evacuated chamber. So basically, we have a chamber or a vacuum that has no gas particles in it whatsoever, and then we have a small hole, and we measure how fast the gas is able to move into this chamber that has no molecules in it. We have an equation that describes this relationship. It's called Graham's law of effusion. The distance traveled by the first gas over the distance traveled by the second gas is equal to the square root of the molar mass of the second gas over the molar mass of the first gas. That sounds really fun, right? So these problems can be a little bit confusing, so you have to definitely pay attention to details when you're working these. All right, so let's look at an example problem. Example problem, helium effuses through a porous cylinder 3.2 times faster than some compound. Okay, so it's telling us, hold on, let me get my pen and go in here. Gotta get a color you can see. Go with pink. All right, so we know that helium is 3.2 times more helium, will you see, it's faster than this other compound, some compound X, okay? So we know that helium goes 3.2 times faster than X. So you'll have 3.2 times as many heliums pass through it as you do X's at any given second. Okay? All right, so that makes helium our first compound, so that means its molar mass is going to go on the bottom. So we got 4.0026. Okay, and then on the top is this unknown compound X, its molar mass. All right, so and I'm going to take out this X because I don't want you to get confused over here. That X was just saying that was some unknown compound. This X is the one we're actually trying to solve for. All right, so to get rid of the square root sign, you need to square the other side. So we're going to do 3.2 squared. Okay, and that's equal to X over 4.0026. So square 3.2, multiply it by 4.0026, and you get the molar mass of 40.99 grams. Okay, so that was the molar mass. Okay, all right, let's look at some more problems because sometimes the wording can throw you off. All right, in this problem it says that we have this amount of NH3 that's going to effuse through a hole in 2.47 minutes. Wants to know how much HCl was effused in the same time. So first thing I would do is I would find the molar mass of each of these. So NH3, when you find the molar mass, it's 17.0307. And when you find the molar mass of HCl, it is 36.4609. Okay, so that tells us immediately we should just be able to look at the sizes. NH3 is going to move faster. Okay, so let's find out what portion of HCl will move through in this time. Okay, all right, so we know that we have some amount of HCl, okay, that will travel through this little tube, and then we know that we have some NH3. So I'm just writing this so we can designate HCl is going to be our first compound and NH3 is going to be the second one. So we get our molar masses straight over here. All right, so we're going to put the molar mass of NH3 on top. So we got 17.0307. Okay, and then the molar mass of HCl on the bottom. Okay, all right, so when you work this out, so you're going to divide and then you're going to take the square root. That's going to tell you that you have 0.6834 HCl's going in for every 1 NH3. Okay, so however many NH3s can get through in this time, this percentage, or 68.34% of the molecules that can get through would be HCl. So take this, multiply it by the moles of NH3, so multiplied by 0.00251, okay, and you get 0.0017 moles. All right, so you need to see if this makes sense. We know that NH3 is smaller, therefore more should move through. This number is higher than this one, so this data makes sense. Okay? All right, let's look at another one. All right, this one says that we have a sample of N2 that's effusion through a hole in 38 seconds. Wants to know what the molecular weight of a gas would be that effuses through this same hole in 55 seconds under identical conditions. All right, so let's find out how much N2 moves through the hole in 55 seconds. So in 55 seconds, our N2 is going to move how much more through the hole? Because we know he can get just as much through the hole in 38 as this one can in 55. And we see that 1.45. So nitrogen travels 1.4 times faster than this other gas that is unknown. So we know that we get 1.45 times N2 to this unknown gas. Okay, unknown gas. All right, so that makes N2 our compound 1, molar mass of 28.014, and this is the molar mass we're looking for. So we're going to do like we did before, square that. So that's 1.45 squared is equal to x over 28.014. 1.45 squared times 28.014 gives us 58.68. Okay, now you have to say, does this make sense? Okay, we know that N2 goes through in 38 seconds and it weighs 28.014, and we know that in 55 seconds, longer time, we can get the same amount of this second one, which is 58.68, so it is bigger. So that does make sense. Okay, so a lot of using this problem is about reasoning through, and if your data doesn't make sense, you go, okay, I calculated something wrong, I need to go back and look again. All right, let's talk about diffusion now. Diffusion is the mixing of gases, and when we talk about the rate of diffusion, we're talking about the rate of mixing gases. So you have two different samples of separate gases, and then you allow them to mix together. The random movement of the gas molecules allows them to eventually kind of mix into one another, like you see in this second picture down here, kind of disperse between one another. The higher the temperature, the faster the rate of diffusion, and the smaller the molecules are, the faster they will diffuse. The larger they are, the longer it will take. So you saw the same type of deal with effusion. Should make sense. They have less velocity, therefore they don't move quite as fast, they don't travel quite as fast. The spreading of a gas through a room, so when somebody sprays perfume, that is diffusion. It's a very slow process considering how fast molecules usually move. They usually move in the hundreds of meters per second. We saw before 410, and then hydrogen 1,920 meters per second. When the molecules collide with other molecules, that's what slows down the diffusion rates. And the best estimate we get for those are going to be through Graham's law of effusion, which is when you have the vacuum. Okay?